When a proton is transferred in a chemical reaction from one compound to another, that's called an acid-base reaction. The compound that gives up the proton is the acid. The compound that accepts the proton is the base. Electrons can also be transferred in chemical reactions from one compound to another. I've written possible electron transfer reactions here. When electrons are transferred, we call them reduction-oxidation reactions, or redox reactions. Here's copper ions and zinc metal, or zinc ions and copper metal. The question is, where do the electrons prefer to reside? That is, will zinc transfer a pair of its electrons to copper and make copper metal? If it did, that would be a reduction. The copper metal, or the copper ions, would go from oxidation number +2 down to 0, a reduction in the oxidation number. Zinc would be oxidized in that process. Its oxidation number would go from 0, increasing to +2. And it turns out that's the spontaneous direction for this chemical reaction. I've written it here. Copper ions and zinc metal, when exposed to each other in solution, say, electrons are transferred from zinc to copper to form zinc ions and copper metal. So in this process, copper ions act as an oxidizer. They remove electrons, oxidizing the zinc. And there'll be a pair, oxidizer-reducer pair, just like in the acid-base case. Once you donate a proton as an acid, you become a base. Same thing here. Once you oxidize by accepting electrons, you have the potential to be a reducer and donate electrons. We can look at the zinc as the reducer here. It's adding electrons, donating electrons to the copper to form copper metal. In the process, it becomes oxidized. And in the reverse reaction, zinc would act as the oxidizer. It would accept electrons from the copper. Itself would be reduced while the copper is being oxidized. Now, this reaction, as I've written, is spontaneous in this direction. That is, the standard state free energy difference is less than 0. And remember, when I say standard state, I mean the state where the copper and zinc ions are at 1 molar concentrations, and there's pure metal zinc and pure metal copper in the system. That standard state free energy difference less than 0 indicates a K, an equilibrium constant, greater than 1. And in this case, it's a large equilibrium constant. It strongly favors the products. And we can see that happen. Here I have copper and zinc. Here's the copper metal and the zinc metal. And I have copper solution, the blue solution of the copper, and zinc solution here. If I put the zinc metal in the copper solution and the copper metal in the zinc solution, let's see what happens. What we expect is this reaction to go in this direction, for copper ions from this blue solution to accept electrons from the zinc, forming zinc ions, and copper metal. And where does the copper metal end up? The copper metal ends up plating out onto the zinc metal. So as I pull out now the zinc, you can see it has a film of copper metal deposited on it. On this side, there's no reaction. This represents the reverse reaction, zinc ions and copper metal, and that's the thermodynamically favored state, is to have copper metal and zinc ions. So no reaction occurs on this side. Now, we can look at the half reactions. We can split up the chemical reaction into 2 half reactions involving electrons. In this case, zinc metal forming zinc ions and 2 electrons. In effect, the oxidation of zinc. That is, zinc goes from oxidation number 0 to oxidation number +2. That's an increase in oxidation number, or an oxidation. That happens, in this case, simultaneously with a reduction of copper ions. The copper oxidation number goes from +2 to 0. That's a reduction in oxidation number. We break these up into what are called half reactions to help us study redox reactions. We can pair this half reaction and this half reaction together, as we did here, or we can compare them with other half reactions that involve transfers of electrons. This will help us study redox chemistry as a whole.